So we're going to look at the area under a curve today. But before we do, let's make one more connection with velocity. So we've got distance from a constant velocity. So we've talked about average velocity. We've talked about instantaneous velocity. Average velocity can go up, down, it can stop, that kind of thing. Whereas instantaneous velocity is the velocity right at that instant in time, what your speedometer tells you on your car. Constant velocity implies that you're not going up or down or changing speed. It's constant, like you would if you were using the cruise control in your car. So we're still going to look at distance equals rate times time. And we have an automobile travels at a constant rate of 48 miles per hour. So constant rate, that means that this is our R. And then we've had this one before for 2 hours and 30 minutes. At 2 hours and 30 minutes, isn't that our time? And that's 2.5 hours. So I have my rate, I have my time. They want to know how far does the automobile travel. Aren't we just using our distance equals rate times time again? Bless you. So distance equals our rate is 40, and I'm actually going to write my 48 like this. 48 miles over 1 hour. Why am I going to write it that way? Yeah, because then I'm going to put my time as 2.5 hours over 1. And my hours should cancel out. And so when you multiply 48 times 2.5, what do you get? 120, and we're left with miles. So you've got a couple of questions that are just simple like that. And the reason why I pointed that out is very similar to example 1 from lesson 11-1. Very similar. Only, remember we started talking about switching. For distance, we replaced it with delta S, which is change in position. And then we kept rate the same, but time got changed with delta time, because we have a change in time or a change in position. If I solve this equation for R, don't I get R equals delta S over delta T? Don't you recognize that? What is delta S over delta T? What kind of velocity? Instantaneous velocity. So there's your roundabout connection. So this is really instantaneous velocity. And isn't instantaneous velocity a derivative? Because instantaneous velocity gives us the general formula for slope of any tangent line to that curve, and that slope is our instantaneous velocity. When I give you, you're going to have a quiz over this next week. I expect you to be able to tell me that. If I ask you what is a derivative, you need to be able to tell me, well, a derivative, because I need to know that you're making that connection. A derivative really means the general slope formula for any line tangent to the curve. And that general slope formula, in an example of what it could be, because slope is rate of change, it could be instantaneous velocity. So we're going to move on to area problems. So a lot of what calculus is about is finding the area under a curve. And so I have a picture here of a curve right here. And then we're going to find the area under the curve by using rectangles. There's actually 6 rectangles here. There's one rectangle right here that's very, very short, because our interval is going to go from 0 to 3. This curve is represented by y equals x squared. So that's our f of x function. So that curve, they've gone ahead and graphed that for you. But we only want the interval from 0 to 3. So I'm going to choose a really light color, the yellow. And technically, I want to go from 0, so here's 0 on the curve, to 5, so here's 5 on the curve. If I connect those, you can kind of see my yellow line here, right? That's the part of the curve that's from the interval 0 to 3. And then this is the interval on the x-axis from 0 to 3, because we always find the area of the curve that's above the x-axis but below the curve. And then this is all the area there that I want to find, all that bit under the curve. So I'm going to take that away, because otherwise on this program it's going to cover up my black lines. But I'm going to go ahead and take that away. So one of the things I also want you to notice is look at where, see if I can get the point on there. Look at that point on that rectangle on that figure. So let me go ahead and get real close. So then look at the point here on the right point on that rectangle, the right point on that rectangle, the right point on that rectangle, on that rectangle, and on that rectangle. What do you notice about the upper right hand corner of each of those rectangles? Yeah, they land on the curve. So this is called right justification. So right hand, oh, I have a feeling that's going to get real small, but that's okay. So right hand justification. And what that means is the upper right-hand side of that rectangle is touching the curve. We're going to look at left-hand justification also, but for right now, that's what right-hand justification looks like. Right-hand justification overestimates. It overestimates the area. And this is purely when we have right justify. What do I mean by overestimating? Because this is all the area that I want is right here, right to here, right to here. I want all that area. So how come it's being overestimated by these rectangles? What's happening here? That's extra area that's being included. So that's what I mean by overestimation. This extra area is being included. And so we're getting a little bit more area than we need to. So we're going to talk about how we could improve that overestimation. In other words, make it smaller by doing something else in a minute. But before we do that, we're going to go ahead and actually calculate the area. And we're going to need some room to do that. So I'm going to zoom back out. Okay. All right, so we're going to create a chart, and unfortunately I don't have the ability to do straight lines, so my line's going to look crooked, but use a ruler. So we're going to look at the interval. And we're going to find the width of the base. And the height of each of the rectangles. Because what's the area formula for a rectangle? Base times height. So I need to know the width of my base, and I need to know the length of my height. And so the area that we're going to use is length, no, not length, because we're really going to be talking base and height, although they're one and the same. So if my interval goes from 0 to 3, so I have 0 here to 3 here. Math Excel, by the way, might ask you to figure out the width of your rectangles yourself. So they might say, you know, here's your interval from 0 to 3, and you have to cut this area under the curve into 6 rectangles. So they're going to ask you to do that. You've got to figure out how to do that. So if I were you, I would write the following. Where am I going to write it? So let's do width of rectangle here equals b minus a over n. And so you need to write the following. I'm not going to write on here because this can get really messed up. But the b and the a right here come from your interval. So this is your b and your a. So this would be my b. And this would be my a. It's always the bigger one is the b because when you subtract these two, you want it to be a positive value. So you find the difference between these two values on your interval, and you divide it by n. N is the number of rectangles that you want to have. So if I want 6 rectangles, here's what we're going to end up doing. So for our purposes here, we had 6 rectangles, so our denominator is 6. Our bigger interval was 3, and our smaller interval was 0, and we're subtracting those two. So what do we get for a width on our interval? Not 2, but what's 3 to 6? 1/2. So that's our width. So as you look at the distance from 0 to 1/2, from 1/2 to 1, let me make this bigger so I can write the numbers bigger. Oh, don't want that there.
You said 6 triangles or 6?
I've got, oh, did I say triangles? I meant rectangles.
No,
Sorry.
no, I meant, is it 6 rectangles?
There's a 6 one right there. It's really short.
Oh, it's 0?
Mm-hmm. Well, it goes from 0 to whatever that point is. And so this point right here is 1/2. So if you plug 1/2 into the function and square it, you get 1/4. So it really has a height. This is a rectangle right here that has a height of 1/4. So it's really hard to see because it's short. And so then the next interval goes to 1, and then 1.5 is 3/2, and then 2, and then 2.5 is 5/2. So if I were you, I would label those as such because we're going to use those in a minute. But the difference between each of those, there we go. The difference between each of these is always 1/2 all the way across. So your rectangles will always be the same width. Their heights, however, are varying in heights. So as we look at our intervals, I have an interval from 0 to 1/2. That's our first interval. And then we go from 1/2 to 1. Still has a width of 1/2. So that's our second interval. And then from 1 to 3/2. And then from 3/2, we're going to 2. And then from 2 to 5/2. And then from 5/2 to 3. Is everybody clear as to where I got my intervals? So there are 6 intervals because I have 6 rectangles. Then our base is really our width. This is my width. What is the width of every single rectangle? What's the difference between 0 and 1/2? The width is from here to here, from here to here, from here to here, from here to here. How far is it in between each of these numbers here? 1/2. So let's put that in, we'll put it in blue. So our base is 1/2 on all of these. Then to find our height, in order to find each of these, see these blue dots? Don't the blue dots represent the height at where that rectangle is? If I look, let's just look at this dot right here at the 3. Isn't the x value 3? How do I find the y value if the x value is 3? Because the y value represents our height. What's the function? Yeah, so use your function. So your height is going to be the value of the function. Your height is f of x. And so we are going to put in, I'll use purple. So we're going to put in f of x here equals x squared. So for all of these to find my heights, I'm going to have to put something in and square it. The question is, what is that something? So that something is the x value at each of those heights. Notice that the x value is always on the right side of each of these rectangles. Doesn't that correlate to the right side of the interval? Aren't these right justified rectangles? So I would think of it in terms of this is the right-hand side, so each of those numbers are going in here. So if we had left-hand justified rectangles, which we'll look at shortly, if we had left-hand justified rectangles, then you would be putting in the left side of the interval into here. Everything else would be the same. The only thing that changes is what number goes into the function. If we're doing right-hand justification, the right-hand part of the interval goes in the function. Left-hand, the left-hand part of the interval goes in the function. And so now all that's left is to figure out what our values are. So here I get 1/4. Here I get 1, 9/4, 4, 25/4, and 9. And then to find my area, we're going to multiply the base and the width together. So all of my bases are 1/2. And then I'm going to put in what I got from my height column. And then do your math. So then that's actually 9. So then what you're going to do is take your handy dandy calculator and you're going to calculate total area. How? How are you calculating total area? You're going to add them together, right? So you're going to take and add all of these values that you just came up with, all my values in green. So take your calculator and add those together. And then you're going to get a decimal in your calculator. Use your math enter button to find out what the true fraction is. And then tell me what you get. What'd you get? Yep, you're just adding up all the ones in green. 91/8? Correct. So 91/8 is also exactly equal to 11.375, and that's units squared. So that represents total area. But remember, that's an overestimation. That's more than what the area really is. So we're going to talk about how do we correct that. Bless you. So as soon as you're done with that, we're going to go write a couple other things down. Any questions on what we got or how we got anything and that kind of thing? Okay. So let's talk about, right over here again. So let's go ahead and add the following. If we were to use the left hand justification, there would be an underestimation, and I'll show you what that looks like shortly, of the area of 6.875 units squared. I calculated that for you by doing the table that we just did. And so I'll explain how that came about in just a minute. I just wasn't going to make you do the entire table again. So we have that written down. Okay, so let's go back to our picture. Okay, so if I were to do the left-hand justification, the only thing that would change would be, instead of using these numbers here, what would I have put here for left hand? I would have put the left-hand side of the interval just here where the purple is. That's all I would have done. That's the only difference. And then we'll draw the picture here in a minute. But you can see if I put a 0 in here and square it, aren't I losing 1/4 of a unit already? So it's getting underestimated, which could be good. And notice that our underestimation was 6.875 versus our overestimation was 11.375. How do I rectify the two? How do I get to a better area? Subtract them and divide by 2. So what did I just find? I heard it. The average. Can't we just average those together, and shouldn't we get a pretty close estimate? So that's what we're going to do. And you're going to write yourself a note. Okay. So the average, can you read that up there? That color? I'll make it darker. All right, so the average between the lefts and right is 9.125 units squared, which is a pretty good estimate. So isn't 9.125 between the 6.875 and the 11.375? It's probably a much better estimate. Still not the exact area. And we're going to talk about how we can get to that exact area. So let's go ahead and look at what would the left-hand justification look like if we were to have drawn it. So underneath here, we're going to sketch it. And so we're going to sketch the very same curve as we have here, and we're going to use this. So we're still going to have to get up to 10 here, so I'm going to have to go pretty small. Making mine just a smidgy bit bigger. We're only going to go to 3. And try to make this just a little bit bigger so that you can see it. Just, this is my 1, this is my 2, and this is my 3. So I can put my rectangles in there. And then my curve should be at 0, 0, 1, 2. Whoops, that's not my 1. 1, 2, and then at at 2, I'm going to go to 4. And 3, I'm going to go to 9. So my curve kind of looks like this, give or take. So this is my y equals x squared. So if I'm going to left justify my rectangles, then that means the left corner of my rectangle is going to end up on here. So like here, and they're only a half wide. It's like here, my rectangle would look like that. And then here, it looked like that. And then this one down on the very left, it's really, the left-hand part's there at 0. And so there's really no height to that one. And so then this one goes this way. So the 3 does not go as high when you finish off at 3. This one does not go as high as that one did because we have a left justification, but we still have 1, 2, 3, 4, 5, 6. But what do you see right here? All of this stuff right here. All that white stuff, that's your underestimation. So you have to pay attention to whether MathXL wants you to left justify or right justify. And it just depends on what type of curve you have, typically whether you make that choice yourself. You can always do both right justify and left justify, calculate their areas, and then divide by 2. Yes?
Can you tell me where you put the points? Because I'm confused.
On the one I just did?
Yeah.
On this one? I put, so at, and I started off at the one at 1. I started off there because it's easier for me to start at 1. That's easier for me to get a height to. So I took my rectangle at 1 and made sure that the left side of that rectangle was touching the curve. And then I went out to the next interval here, which stops here, right? Because my next interval here is at 1.5. And so then at 1.5, I want to make sure that that point is right there. So technically I have another point here, right? And another point here. I just didn't put those on there. And a point here. So each of these points are the left-hand side of that rectangle. And it's really hard to change that justification because some of us are right and left brain oriented, and you're going to find that one is easier than the other for you to draw. For me, it's easier for me to draw the right-hand justifications. It's much harder for me to draw the left hand. But that's normal. It's just how your brain is wired. Courtney? The average, you're just going to take the right hand and then what I gave you for the left hand, because you didn't calculate that, I did it for you, and then add them together and divide by 2 to get that 9 point whatever. So you're just averaging them. Any other questions? Okay, so before we go on, let me talk about something else. So I'm going to take my original picture right here. And so we got our area, right? But I'm going to make this really, really big because I want you to see what's going to happen. What would happen if I instead had 12 rectangles rather than 6? So I'm going to go ahead and partition this into 12s. And I think I'll use red. So that means I'm going to cut every rectangle in half. And so, like for instance here, I'm going to have a partition here, 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 and here. Those are going to create 6 more rectangles. So that means I have my left side here, and then here I have a left side. This one's really hard to see. It's really little. And then this one, I'm going to go from here to here and down, and then from here to here, down, and then from here down, and from here down, and then from here down, and from here down. Whoops, missed it, sorry. Missed it again. I'm an excellent drawer. So what do you see happening here with all the overage? What do you see happening now? It's reduced. My overestimation is reduced when I have 12 rectangles, isn't it? So is my estimate with 12 rectangles better or worse? The more better, right? So what's going to happen if I change the 12 rectangles into 24? I'm going to become more precise. And from 24 to 48, more precise. 48 to 96, more precise. Essentially, aren't I going to eventually approach the actual area? Doesn't that sound like a limit to you? When I approach a number, doesn't that sound like a limit to you? It should. And so the theory comes that if I had an infinite number of rectangles in there, shouldn't I get the exact area? The problem is, how do you get an infinite number of rectangles in there? So the integral was devised, and so that is your next page. So I'm going to go ahead and take this off if I can. Oops, do it again. Yes, perfect. All right. So the point is, the more rectangles we have, the better our estimation is. So look at the back. So we have what's called the definite integral. It's just new notation for you. And what that notation is, it's right down here. This is the most important part of the definition of that notation. The rest of this notation here is describing what we just did. So this notation, this little funny S represents the word integral, and the A and the B is your interval. So in our last part, we're going to do an integral from 0 to 3. Wasn't that our interval? And then this f of x is the function, the line, the curve that we're finding the area under. I'll talk about the dx in a minute. But notice that it says, what's this thing right here? A sum. Didn't we just take the area of rectangles and add them together? Isn't that a sum? Yes or no? That's what an integral is. It's a sum of the area of the rectangles under the curve. But our hope is that we have an infinite number of rectangles under that curve, because that gives us the most accurate answer possible. And so here comes my definition to what dx is. So remember, dx is part of the notation for derivative, isn't it? Remember the derivative dy dx? All that this is, go ahead and write this down, then I'll explain. It's an infinite small width of rectangles. It just means that as I increase my number of rectangles, the width of those rectangles are getting smaller and smaller and smaller. They're getting infinitely smaller and smaller and smaller. And so that D really means delta x. D for delta x. So go back to what our derivative notation was, dy over dx. Delta y over delta x. Isn't a derivative a slope? Isn't slope change in y over change in x? Do you see where Leibniz may have come up with that notation for a derivative? Because what is a derivative? Slope, right? So it's all coming to full circle here. All right, so let's go ahead and look at how do we actually use this. You're going to do the math for the integrals whenever you reach calculus. So we're going to just start with the easy integral problems, and we're going to view these as area problems. So let's look at example 3. We're going to approach this as if it's an area problem. You'll see why in a minute. So, view as an area problem. It's going to require your knowledge of geometry. So we're going to sketch what we have. And what this notation is telling you is we're going to take the integral, the sum of the rectangles under the curve, from the interval of 1 to 5 on the x-axis. So these are our markings on the x-axis. And this is our f of x right here. F of x equals 2 of x. And this is just the additional notation saying that we want infinitely small widths to those rectangles. So we're not just doing 6 rectangles, we're doing an infinite number of rectangles. All right, so let's just go ahead and graph f of 2x. What kind of a graph is that? It's a straight line. So if I'm going from 1 to 5, these are x values, this is our y value. So plug 1 into 2, what do you get? 1 into 2x, what do you get? 2. Plug 5 into 2x, what do you get? 10. So we have to go up to 10. So on this axis here, we have to go up to 10. So write small. And I have to go at least out to 5 on my x-axis. So if I had a straight edge, which I don't have the ability to do that on here, that would be a very straight line, wouldn't it? But we only want to find the area, according to the integral, it's telling us you want to find the area from the horizontal axis, which we're making the assumption is the x-axis for now, to that curve, but only an interval from the x values of 1 to 5. So we're going to cut this off and make vertical lines from 1 and 5. So what that does is it creates a shape. And I'm going to shade in this shape right here. What shape is that? What shape do you see? It's not a triangle. If we went from 0 to 5, it would have been a triangle, but this part's missing. It goes from this straight edge to that straight edge. These are parallel lines from here to here. Turn your paper 90 degrees and tell me what it is. It's a trapezoid, isn't it? Because it's got one set of parallel lines. These are the parallel lines. I guess I could actually turn this. Look at it this way. Doesn't that look like a trapezoid? Now you've got your parallel lines here and here, right? So that's your true definition of a trapezoid. So you do have to be able to recognize what you have. That is the coolest thing. I can turn my paper on here. Love it. I know that wasn't very exciting to you. Things that make a teacher happy. All right, so this is a trapezoid. It is assumed that you know the area formula to a trapezoid. Anybody know? Almost. 1/2 sum of the bases times the height. Very similar to a triangle, right? But you have the sum of the bases. But we have to find those measurements. So our bases, again, are right here and here. What is the distance from here to here? So in other words, at an x value of 1, what's the height? Don't you plug it into the function? What's 2 times 1? 2. So the height from here to here must be 2. The height is always the y value. So this must be, that's b sub 1 is equal to 2. What about b sub 2, this height, this base right there? What's the height of that, if you will? Yeah, plug 5 into the function, so 5 times 2 is 10. So b sub 2 is equal to 10. Now the only other thing we need is the height of the trapezoid itself. The height of any figure is always the distance between the bases. These are the two bases. What represents the distance? From here to here. Yep, so from 1 to 5 on the x-axis, what's that difference? 4. So that means that our height of the trapezoid is equal to 4 units, and it's from here to here, so from 1 to 5. How do I know it's from 1 to 5? That's the interval, from 1 to 5. And so you're going to plug all these values in. So our b sub 1 is 2. Our b sub 2 is 10. And then our height is 4. So we get 1/2 of 12 units times 4 units equals 24 units squared. That was a lot better than making rectangles. We did not over or underestimate because we have the trapezoid is the exact area that we're looking for under that figure. So this is just another way that if you have a area under that curve or that function that is a recognizable shape, we can go back and fall back on our geometry rather than have to make all those rectangles. Yes.
I don't know where you got the 2 and 10 from.
The 2 and the 10 came for those parallel bases. So remember, these are the bases that are parallel to each other. And so to get the 2, I want to see, well, how high up there, because that height right there, just like the height on the rectangles, is what's on the y-axis here. If you want to find out what the height is, you have to take the x value at that point, because I know that that point has an x value of 1. To find the y value, plug it into the function. Because technically, this is an ordered pair in the coordinate grid, right? So if I know the x value, just plug it in the function to find the y. That y value represents that height. And that's what we did over here to get the 10. Our x value at this point here is 5. Just plugged it in to get the 10. Anybody else have questions on that? So then the last example, we're using the same function, you'll see, because we've got a function of 2t. It says, suppose a ball rolls down a ramp so that its velocity after t seconds is always 2t feet. This is actually f of t. It's f of t because we're using t this time, not x. So that means that y is equal to 2t. Isn't that the same as y equals 2x? But our interval is different. Our interval here, they want to know how far it fell during the first 3 seconds. So our interval is from 0 to 3 seconds. As I said, the first 3 seconds. They didn't say from second 1 to second 3. The first 3 seconds include 0 to 3. So we're going to write our own integral. I have a really fun time writing those integrals. So I'm being facetious. Looks like an S. Well, not bad. 3rd time today, doing well. All right, so that our interval always goes from low to high. So our low number on the interval is 0. Our high number is 3. So that's our A and our B. Then our function is our f of t. Well, our f of t is 2t. And then we want to tack on not d of x, but d of t, because our variable is t this time. And that's just saying that I want an infinite number of rectangles with an infinitely small width, delta t. That's the distance of that width of the rectangle. All right, so we're going to sketch our graph, and we're going to use area rather than rectangles. We're going to use geometry area rather than rectangles in order to find this. So again, this time put in 3 into your function. So put 3 into 2t. What do you get? 6. So I only have to go up to 6 this time rather than 10. So we're essentially graphing the same thing that we just did. And I only have to go up to 3 on the x-axis. So plot your points, or your graph, however you want to do it. So this is y equals 2t. And then I have to go from 0, well here's 0, to 3. So this time my shape is what shape? This time it's a triangle, right? What's the area formula for a triangle? Yeah. Area equals 1/2 base times the height. Remember in a triangle that your base and your height are always perpendicular to each other? And this is a right triangle, so aren't the legs the perpendicular parts? What's the distance of this leg from 0 to 3? What's the distance from 0 to 3? 3. 3 minus 0, 3. So this is 3 units from here to here. So that's going to represent our base. And then what's our height from, what's our height from here to here?
6.
Yeah, put 3 in there that has a height of 6. So your height here is 6, and this is our base. So we're going to plug in our values. Our base is 3 units, and our height is 6. That's actually a 6. And so we get, what, 9 units squared. So it's the same exact thing, but our integral change, our interval change, which changed the shape of that figure from a trapezoid to a triangle. Sam?
Isn't it how far it is falling?
Say that again?
It says how far is it falling in the first 2 seconds? It can't fall.
Area on the curve represents that distance.
So is it units squared?
Oh, I see what you're saying. Yeah. I see what you're saying. It is. It's nine, yes, units. You're exactly correct. Yeah, you're right.